It is chapter 9, Vector Spaces and Orthogonality. In this chapter, we'll study a little bit more of linear algebra. Here the major subjects are Gram-Schmidt process, QR factorization, and QR iteration for finding eigenvalues. Let's begin with section 9.1, subspace of Rn. A subspace of Rn is any set H in Rn that has three properties. The zero vector is in the set. For each u and v in H, the sum is in the set. For each choice u in H and for each choice of scalar c, the scalar multiplication is in the set. If these three conditions are satisfied, then the set is a subspace of Rn. These three conditions can be expressed with this one line. H is closed on the linear combinations. Then it should have a zero vector, and it must be closed on the addition and closed on the scalar multiplication. Rn itself, with the standard addition and scalar multiplication, is a vector space. See the example. A line through the origin in R2 is a subspace of Rn. If we consider a line in two-dimensional coordinates, so let's draw in this way. And once you choose, of course 0 is here, and if we choose two vectors on the line, then their summation must be on the line. And scalar multiple, of course, the result is on the line, so that it is a subspace of R2. Any plane through the origin in R3 is a subspace of R3. And you can easily check that linear combinations of vectors in this plane are on the plane. And this plane can be expressed as the span of two vectors, v1 and v2, and v1 and v2, then their linear combinations will make this plane. v1 to vp is in Rn, then span of the vectors is a subspace of Rn. By definition, the span is the collection of linear combinations, so that the set must be closed on the linear combinations because it's already having every possible linear combinations. So it is a subspace of Rn. Every spanned set in Rn is a subspace, right? Given a matrix A in R n by n, we may consider the subspace spanned by the column vectors of A. In this definition, the column space of a matrix is defined. The column space of A is the set, and we are using the notation call A, the set of all linear combinations of columns of A. Once A has n columns, then call A is the collection of linear combinations of columns of A. And here C1 to Cn are arbitrary scalars. So this call A must be a subspace of Rm. Each vector each column must be in Rm, so that their combination must be a subspace of Rm. A is given and B is given. Determine whether B is in column space of A. Okay. Once A, okay, now once B is in column space of A, that means that B is a linear combination of columns of A. So that condition is the same as that one, which means if we consider the linear system AX equal B, then this system has a solution. And we can find some quotients so that the scalars, so that the linear combination of columns of A with the quotient, the weights, becomes here right side B. The system is consistent, is the same as this augmented metric has a solution. So to solve this problem, we may begin with augmented metric. Okay, let's do that. Now A, 1, minus 3, minus 4, and minus 4, 6, minus 2, minus 3, 7, 6. And right side, 3, 3, minus 4. Okay, now we apply elementary row operations and try to see if it has a solution. Okay, first one is 1, minus 3, minus 4, 3. That's the first row. And we eliminate the quantities below the pivot. And 4 times addition will be 0. 4 times addition, minus 6. 4 times addition, that is minus 16 and minus 18. 4 times addition, which becomes 15. Now 3 times addition must be 0. 3 times the addition, minus 2. 3 times addition, minus 6. 3 times the addition, that must be 5. Okay. Now from here, okay, we may eliminate this row because that is simply 3 times of the last row. So that from here, we can get 1, minus 3, minus 4, and 3. And then here 0. Okay, we multiply possibly minus 1. Then 2, 6, minus 5, and 0, 0, 0, 0. Okay, we have a pivot here, and there is a free variable, and x3. And so that in fact, we have infinitely many solutions for this system. So that that means now B is in the column space of A. So you can finish computation to get explicit quotients. A is an m by m metric. The null space of A, we are using null A, the notation, is the set of all solutions of the homogeneous system. So collection of X satisfying AX equals 0 is null space. So null space is a subspace of Rn. Of course, null space in the beginning must be subset of Rn. First of all, now, okay, let's start with the 0. And null of A is a subset of Rn. And firstly, 0 must be in the set. Because here, if you put here 0, then it is satisfied. And secondly, now we have to show it is closed under addition. Then if you choose U and V from null space of A, that means and AU equals 0 and AB equals 0, so that they are in the null space. So here, if you add, so the AU plus V, then AU will be 0, AB will be 0, so that is 0, which means U plus V is in the set. Right? If we check this separately, these conditions, then we can do this way. And finally, we choose U from null space of A, then AU equals 0. Now, AU is 0, then any scalar U must be 0. So that means CU must be in null space of A. Right? So it is closed under addition and scalar multiplication, and 0 is inside the set, so that null A is a subspace of Rn. Basis for a subspace. A basis for a subspace H in Rn is a set of vectors that is linearly dependent and spans H. For example, for R2, here, with these two vectors, we can span R2 for arbitrary vector in R2, and you can find the coefficients such that it becomes the vector. Because if you try to get a matrix from these two vectors, 1, 0, 1, 2, then the coefficients will be arbitrarily chosen vector, right side in R2. Let's say that is B. Then these coefficients can be decided. You can see easily this is invertible. So the C is determined uniquely. So it is always we have that, which means these two vectors span R2, but apparently these two vectors are linearly independent. And linear independence can be checked along with the corresponding matrix. So if you have the pivots and the same number of pivots, there are two vectors, not two pivots, so that they are linearly independent. Okay, now we consider E1, E2 up to En. So E1 is, first component is 1, E2 is, the second component is 1, and so on, so that En has 1 at the last entry. Then this vectors is called the standard basis for Rn because these are standard coordinate vectors. In R2, that is, one is here, E1 is 1, 0, and E2 is now 0 and 1. These are standard vectors, standard coordinate vectors in R2. So we say the collection of these vectors is the standard basis for Rn. Find a basis for column space of A. Okay, column space of the matrix B, not A. Okay. Now, if you try to get linear combinations of columns of A, then that is column space. But a basis must be here the independent, linearly independent subset of a column. You can find them here. If the metric is given in this way, then this is pivot, this is pivot, this is pivot. It's already in reduced echelon form, and they are pivots. And here there is B1, B2, that is B1, B2, and that is B3, B4, and B5. Then you can easily see that B3 is a linear combination of B1 and B2. Here that is exactly this one, minus 3 times of B1 and 2 times of B2. That is B3. For B4, 5 times of B1 minus B2. Then there is B4. So these two can be generated. Once we eliminate these two vectors, then the three are linearly independent. So that these three vectors form a basis for the column space. And we say here in the theorem, in general, non-pivot columns are linear combinations of preceding pivot columns. As in this metric, here this one is a non-pivot column. This is linear combination of a preceding pivot columns, B1 and B2. And also for this one is a linear combination of preceding pivot columns, B1 and B2. We can see quite easily. Thus, the pivot columns of a metric A forms a basis for column space A. For pivot columns, they are linearly independent, and also because non-pivot columns are expressed as a linear combination of pivot columns, we don't have to worry about for spanning set. So only we consider pivot columns, then they are linearly independent, and they also can span the whole column space of A. So pivot columns of a metric form a basis for column space of A. Find the basis for the column space and the null space of the metric A. Okay, that is a metric. And with some elementary row operations, we can reach this reduced echelon form. Now, first one and third one, these two columns are pivot columns. In fact, not this one. You have to select the columns from the original metric. That one are the pivot columns, and collection of these two columns will be a basis for the column space of the metric. Okay, so that these two vectors will form a basis for the column space. Okay, now we have to find here basis for null space. That is the same as this one. In fact, the null space is collection of x such that ax equals 0. This one is obtained from elementary row operations, yet this metric times x must be 0. So we have to collect x satisfying this homogeneous equation. But from the first row, we can see that here x1, x2, and x4 are free variable. So equal minus 2x4, x2, and minus x4. Now x2 is free variable. So now we'll decide this one later. And x3, the line, is saying that that is minus 2x4, and x4 is also a free variable. Okay, to decide this one, we may say that x2 is x2 and x4 is x4. Right? Then from here, x, the vector of x1 to x4, that is same as x2 can be chosen arbitrarily, and then here now the first component is minus 2 and 1. These are zeros. Along with x4 is a free variable. You can choose it arbitrarily, and there's minus 1. This must be 0. Second one must be 0, and minus 2 and 1. Right? So x, the solution of ax equals 0 for the system, this is the general solution. x2 and x4 are free variables, so that you can choose them arbitrarily. That means the null space is now spanned by these two vectors. Eventually, the collection of linear combinations of two vectors, so that you write down here, and one vector minus 2, 1, 0, 0, and another vector that is minus 1, 0, minus 2, and 1. So that's the null space of A. Okay? Basis for null space of A can be obtained from the parametric vector form of solutions of Ax equals 0. Right? We try to find the basis for null space of A by solving Ax equals 0. Exactly, we did that. That is, suppose that the solutions of Ax equals 0 lead that one. So here x1 to xk correspond to free variables, and we rename here now the x component scalars. Then we can write in this way. Then basis for null space A is the collection of the vectors here u1 to uk. Exactly we did in this example, right? Okay, now we'll see the rank theorem. A is an m by n metric. Then dimension of column space of A and dimension of null space of A, the addition must be same as n. Dimension of column space A is the number of PV columns, and dimension of null space of A is number of free variables. So that if you sum, then that must be the number of columns in A. We call this one as rank. So that rank A is dimension of column space of A. And for this second part, we usually use the term nullity. The nullity of A is dimension of null space of A. So the addition must be n. Rank plus nullity must be n, which is the number of columns in A. Okay, we'll continue in the second section. Thank you.